Okay, so thanks for the invite. You know, since this is the last talk and I didn't want you to forget, I decided that I'm going to talk about memory. And so or the memory premium. This is joint work with York Spenkuch and David Almog. And the question that we ask, should I turn it? No, I think, oh, it's the other. This is the clicker? Okay, thank you, Bary. So, so the type of situations that we have in the paper is we are thinking about a decision maker who made many choices in a fixed environment. Now the decision maker is facing a new and unfamiliar environment. And the question that we are asking is, how does the decision maker choose in the new and unfamiliar environment? Now, this is a big question. We are going to make modest progress by looking on one aspect, that is memory, and study how memory from the familiar situation, how it affects choice behavior in the unfamiliar situation, okay? And the answer that we are going to give is that decision makers exhibit what we call a memory premium. They tend to choose alternatives that they chose in the past. But importantly, even though when these alternatives are objectively inferior. So we are going to have a metric of objective value, and what we are going to see is that decision makers choose in-memory alternatives even though they are inferior in terms of value. Now, after we establish that, there is a natural follow-up question, which is why do decision makers exhibit a memory premium? And here I'm going to suggest that the premium results in part, okay, I'm not going to argue that this is entirely what drives it, but that the premium results in part from decision makers' tendency to prioritize in-memory alternatives. They just consider them first. And once your choice procedure starts with thinking about in-memory alternatives, it's sufficient that you choose a good enough alternative in order to see a premium. And our third result in the paper, so it's a big project. I'm going to cover, I hope that I'm going to cover the first two bullet points. The third thing that we do in the paper, in this project, is that once we realize and once we convince ourselves that memory is important to choice in unfamiliar situations, we can take research on memory that was done mostly not for choice behavior, and then think about what type of regularities we expect in choice based on regularities in memory. And so we have 4 attributes that we consider that I put here on the slide, and they are, and so we have predictions that map research on memory to how it's going to manifest itself in choice behavior, and we show that this type of predictions about choice behavior hold. Okay, so this is the project. The way that we are going to proceed, I'd like to define first. I'd like to define formally what I mean by a memory premium. Then we are going to move to test whether there is a memory premium in a game called Chess 960. I don't know how many of you know Chess 960, but the idea is that this is a game like chess, the same pieces, the same board, the same rules, only that the players get a randomized version of the pieces on their back rank. Okay, so we are going to talk about exactly why we choose this, this game and establish the memory premium in this setting. And after we do that, I'm going to report an experiment that actually we got the results last week, or I would call it a pilot experiment about the mechanism. Okay, so that's the plan. We are going to start with the definition. In order to define the memory premium, I will need a few more definitions. So a choice situation is simply a pair as written on the board. These are the alternatives available for choice and the environment. Okay, so now the environment, right, the decision maker made choices in some environment, so the environment didn't change. Now the environment changes, and potentially the set of alternatives changes, and then the decision maker needs to make a choice in the new environment. Key is that an alternative's objective value, okay, that we are gonna that we will know as an empiricist, and that the decision makers may or may not know it, is a function. It depends on the environment. Okay, so a particular alternative in different environments would have two different objective values, potentially. Okay, so this is one primitive, and now since we are going to talk about memory, I will need to define what I mean by memory. And so let me remind you that the decision maker made choices in a fixed choice situation, so I don't need to carry around the choice situation, okay, because I know it. So the decision maker's memory, and that's for simplicity, okay, of course it can be enriched, it's just that what I'm going to do here, I don't need to enrich it, and so for simplicity, we can think about the decision maker memory as a vector of all past chosen alternatives in the familiar environment. So the first component in the vector is what the decision maker chose 1 period ago, and then 2 periods ago, and so on. And an important piece of notation is M plus A. So M plus A is a memory, okay, so it's a memory that obtained from the memory M by adding to it one or more instances of the alternative A. So you take the memory M, you look at an alternative that is not in memory, you add it to certain places in the vector. I'm going to call that M plus A, and there are going to be, right, there is going to be a set of these M plus A's.
Memory is ordered. Memory.
Yes. Yes, it's vector. Yes, it's a vector. Yes.
So the order matters.
Of course, of course.
No, that's good.
But I put it like Sergio vector.
So a decision maker remembers what she did in the past, but she doesn't remember what her payoff from that decision is?
That's why I said, Eric, only for simplicity.
Okay.
We can add the payoff, or let's call it the outcome, but I don't need it for what I'm going to do. Okay? And it will become very clear because I changed the environment. Right? And what I care about is the payoff in the new environment relative to the payoff in the old environment. Given that this memory given that this alternative sits in memory, okay, this is just for simplicity. Actually, in the paper, we define memory as a chosen alternative and the payoff. Okay. Yes. Okay, and you will see, I'm going to keep going, and you will see that I don't need it. Okay.
Okay. If in the world that's trained us, then we may have developed a heuristic to continue to choose things we've chosen before. Your experiment may have negative correlation among requirements, I don't know. But
Exactly. Yes. So Meg, this is this is part of what I'm not going to show you today. You predicted right. We would expect that the construct that I didn't define, which is the memory premium, is going to be a function of the distance between the familiar environment and the new environment. And actually, we have a metric for that, and we have like a graph. I would say it's a beautiful graph, but I'm not going to say that. Yes, and so, and it's exactly what you said. Based on how you would not, you Meg would naturally define the distance. Okay, so the object of investigation is a random choice function that takes a choice situation and an alternative, and it conditioned on the memory status, right, on memory, and it assigns to every alternative a choice probability, okay, which will vary with the memory of the decision maker, okay? Now, why are we assuming random choice functions? Because, well, we know that for memory research that retrieval from memory is probabilistic, and we also think that value assessments are noisy, especially when the alternatives are complex. Okay?
A choice situation that is given includes a full list of the available choices.
No. A choice situation is a set of available alternatives and the environment. It's not a list, it's a set.
But when you give it to people, you cannot give it as an, I mean, in an experiment or whatever, you give it in some order.
I'll show you the experiment, yes.
You randomize over the order in which you present it.
Yes.
Okay.
Okay, so when did we start? 21 minutes left? Okay. Okay, so Sergio, no questions anymore. Okay, so.
Forget this after 1 minute.
Okay, so I'm going to define the memory premium. I'm going to use delta to define the difference in choice probability as an alternative enters memory. And I'm going to say that the choice function gives rise to the memory premium if for every choice situation, for every memory, for every alternative that is not in memory, and for every m plus a, which is the memory plus either one or more instances of the alternative, I have these equations. The change in the choice probability of the alternative when an alternative enters memory is positive. And I'd like to say that it's large, which is I'm going to say here in the second bullet point, that the change in choice probability as an alternative enters memory is larger than the change in choice probability of any other alternative. And yes, Sergio, you are right that the first part of the definition, I think it's a consequence of the second part of the definition, but I still need to check that. Okay, so let's move to the setting. So actually, we are going to test this. We are going to test the memory premium in a setting that was actually designed to reduce the reliance of decision makers on memory. And that's the game of Chess 960. Chess 960 was invented by Bobby Fischer in '96 in order, because Bobby Fischer felt that that players of chess put too much emphasis on memorization and less on strategically thinking. And so he said, let's randomize the board. Okay, and okay, so that's the key departure. It's called Chess 960 because the randomization has to be according to particular rules, and this generates 960 configurations. Let me show you a visual. So I think Yeah. This is, trust me.
Some additional constraints.
Trust me. There are constraints. Okay. It's actually a nice it's a nice combinatorial exercise for first course in discrete mathematics. So if you are teaching, that's okay. So here is a visual, okay, and here is a visual of this game. I'm going to leave it on the board for a few seconds. I just want to point out that the positioning of the pieces on the back row of the players here, no piece is in its position as in regular chess. Okay, so this is just an example.
And they're the same for both?
They are the same for both, yes. Yes, it's a mirror image, yeah. Okay. So why do we look at chess 960? So first, it's an unfamiliar environment with the qualification of Meg. It's either more unfamiliar or less unfamiliar, and we view it as an advantage because we can tune up and down the level of unfamiliarity. And most importantly, we can approximate players' memory and the objective quality of moves. So what's memory in chess 960? It's what you played in chess. Okay, and what's the quality of the move? Those of you computer science, I think that, or if you play chess, you know Stockfish. Stockfish is a very, very powerful chess engine. I think its ELO rating is 3,400. It wins 99 out of 100 games against the world champion. And what we need to keep from Stockfish is that these are integers. A positive integer means an advantage to white, negative an advantage to black, and it measures in 1/100th of a pawn, so it's called centipawns. That's the currency. Okay. So now we are going to move to that's the empirical part. I forgot to say that. We look at data from a platform called lichess.org, which is, those of you who play online chess recognize it, I think. It's one of the big platforms. Lichess hosts millions of games of regular chess every day and thousands of games of chess 960. We use data from over 8 years. And in our main analysis, and then we do a lot of robustness check, but in our main, and I would say cleanest analysis, we restrict attention to opening moves of about 150,000 players. We are going to look at the first time that they play chess 960 as white. And the game is rated, so players care about it. And in order to measure memory, we are going to look at players, so this is the 150,000, with at least 20 standard moves. Okay, so that we see the history of play. Okay, this is the main result. What I am plotting here is for every centipawn rating, right? This is a bin scatter plot, but what we do here, we have 20 bins, and then we match the centipawn rating of the move, and we compare the choice frequency of the move with this rating for in and out of memory moves. Okay, so what we see is that alternatives that are in memory are much more likely to be chosen. And we also see that as the quality increases, the choice frequency increases. That's good. It means that Stockfish is doing a good job, not surprisingly. And what's striking about that is that even the best out-of-memory move is chosen less frequently from the worst in-memory move. Okay? and the average difference between these two lines is 12%. Now, I'm cheating a little bit here because this is the raw data, and so we need to account for factors that may be correlated with these numbers, and so that's what we do. That's what we do in the regression analysis, and so in the regression analysis, we look at a particular board position, a particular move in that board position, which means that we are going to fix the objective quality of that move and all other moves in the board position. And then we are going to see the difference, the memory premium between across players with the same rating, with the same memory size, and with the same number of games. And what we see here, I'd like you to look at column 6, which has the most controls. We get 4 percentage points, which is still very large because the average choice probability of a move is 5 percentage points. Okay? So I think that's the memory premium. Okay? Now, yes?
So the memory is the opening move, is that what is remembered?
Yes, what is remembered is the vector of all, thank you, Ehud, is a vector of all the history of opening move in standard chess for this player. And then we look on the first game of 960, what did this player play? Yes?
Could there be a selection bias in the fact that those people were probably winning more than losing, because if you lose, you stop playing and you get out of the site. The fact that they are there, probably they were winning more. Those are the things that the players that were repeating were playing many times. So maybe since they are winning, you don't change a winning team. That's a saying. So you keep playing those things because you are winning.
I'm not sure, Sergio. We have to be careful here. There are many alternative mechanisms. What I showed you is that when we control for everything, right, including ELO rating, including the quality of the player.
But you can control for winning or losing the game, which I think, what Eric asked also, it's the same game that you are playing. I think that should be clearly something you want to control of. You won the game, then you started with some move, then probably you'll play it again. You lost the game, maybe you'll play something different. That's the first mechanism I would use.
No, but you played standard chess, Sergio. So what do you want? You want the last strategy that.
You have in your data also whether they lost or won.
But you only have one data point, right?
No, he has 20. He said they played at least 20 times.
It wouldn't matter. It wouldn't matter. No, I'm saying I don't show you. Like I said, okay. It's a possible mechanism. I don't think that's what's happening in the data. Yeah. Uh-huh. Which is why. No, the strategy is to say no questions for Sergio, and the idea is that he's going to reduce the number of questions. I know. Okay, so Sergio asked about the mechanism. What is the mechanism? Okay. So in order to do that, and that's in line with what Colin said, we want to go to the lab, okay? And we want to try and identify the mechanism, okay? Now, big picture, okay? Now, maybe it's included, maybe Sergio's mechanism is included, maybe not. I would say that big picture, there are two classes of mechanisms that could generate the premium. The first one is that decision makers just assign higher value to in-memory alternatives. Maybe because they won with them, okay? Maybe. But they assign higher values. Now, why would they assign higher expected values? Maybe they extrapolate from the outcomes in regular chess. Maybe they have more concentrated beliefs about actions that they played in the past. Maybe, I don't know, but certainly this is a possibility, okay? Now, the other possibility is that this thing is procedural. And what do I mean by procedural? I mean that decision maker prioritize the consideration of in-memory alternatives. They just consider them first, and they don't maximize. They consider them first. If they are good enough, they are going to choose them. So this is an alternative mechanism, which sometimes it's called satisficing, sometimes it's called rational search, depends on how the threshold is defined and so on. So how are we gonna distinguish between these two mechanisms? We are not going to distinguish between the two. Instead, we think that the procedural mechanism is less in line with standard theory, and so we are going to shut down the subjective utility mechanism, and inspired by Collins' work, we are going to design the experiment in a way that we can follow the order in which decision makers are going to evaluate the alternative. Okay, so the experimental setup, so this is 200, this is a pilot, 250 50 participants, playing 20 rounds of what we call an investment game, and they are rewarded based on the value of their investment in one round of the experiment. And each round is composed of two stages, the research stage, when we are going to induce memory, and the choice stage, where we are going to ask participants to choose among the 3 randomly selected companies and 3 more. Now, everything is random. Whatever you think about how to randomize, we randomize it. Okay, so we randomize the payoffs, we randomize the discount or the growth factor, what we call. Everything is randomized. The order is randomized, everything is randomized. Okay, let me show you an example of a round. So in this round, okay, so this is the research stage. We asked players to calculate the profit of 3 companies. How is profit calculated? According to the formula that appears on the slide. In order to pass this stage, players have to calculate the profit correctly and then click the next button. After they click the next button, there is a short delay of 15 seconds, and then we show the 6 companies. Okay. Again, random order, not the same as in the research stage. Everything is randomized here. Okay, and then they see 3 more companies. Now here we say, look, the total value, the way that you are going to be rewarded based on, is the total is the profit, which is the expected value, times the growth rate, which is distributed uniformly between between half and 1 and 1/2. So in expectation, what you saw as the expected value is going to be the realized value in expectation, but in order to figure out, you need to click the evaluate button, see the growth factor, and only then it switches to choose. You can evaluate as many alternatives as you want before you make a choice, and the only constraint that we are asking is that you evaluate the growth factor before you are able to choose. Okay? Questions about the design? Okay, so now we can see when they click the evaluate button, we see the order of evaluation. Okay? Okay, so I have 2 slides of the result. The first slide is not going to be satisfactory. It's just I'm just showing it to you, but then I'm going to go to the second graph, and I think it's going to be clearer and cleaner. okay? Okay, so we see a memory premium. Okay, now before we, yes?
How important is it that you are time constrained?
I'm sorry?
How important is it that you are time constrained?
It's not important. It's not important. We do see subjects, participants clicking less alternatives when they are time constrained, but it's very minor. And actually, we are thinking about just removing the time constraint. So thank you. Okay, so we see a memory premium. Okay, now my co-author likes plotting graphs that start from 0 and go all the way to 100. And so this is a big effect. Okay, this is a big effect. It's about half of the 13%. It's a big effect. So the alternative is more likely to be chosen if it's in memory. It's more likely to be evaluated if it's in memory. And it's more likely to be evaluated first if it's in memory. Now, why did I say that it's not satisfactory? Because there is a good reason why you want to start with in-memory alternatives, which is that you see 3 companies, and the highest order statistic is give or take 8.3. I think it's give or take 8.3. Now, that's higher than the expected value of out-of-memory alternatives. So you better start with this alternative, right? That's in some sense in the spirit of rational search. But, so that's why we are going to plot for each expected value of the highest order statistic, we are going to plot whether we see these numbers, okay? So we are going to compare in the next graph, we are going to compare the choice probability relative to the average out-of-memory alternative evaluated and evaluated first. And since I don't have much time, I want you to focus on expected value of 5. Okay, so expected value of 5, and I anticipate that even for an expected value of 4, we are going to see that because we have fewer subjects, and the likelihood that the highest order statistic is low, and so we don't get many observations here. But even for an expected value of 5, we see the memory premium and the idea that decision makers prioritize in-memory alternatives. Now, what's puzzling about that is that you are better off by clicking the evaluate button of any out-of-memory alternatives and then choose it without doing any calculation, because the expected value is 6. So decision makers go for 5, while in one click they could get 6 without doing any computations. Okay? And so I think that when you look at 5, it starts suggesting that this is not exactly rational search, whereas the monotonicity of frequency, it does suggest that there is a flavor of rational search, but it's not enough to explain what's happening, certainly in 5. Okay? So to summarize, in new and unfamiliar environments, people tend to choose in-memory alternatives, even when they are objectively inferior to out-of-memory alternatives. And this memory premium results in part, right? So we are not ruling out the subjective utility. We actually think that in our data it's present. It cannot be present in the experiment because we induced objective values, right? They try to maximize their payoff in the experiment. So this memory premium results in part by the tendency of decision makers to prioritize in-memory alternatives unless they are bad, right? Which is what I refer to as 4-2. Yes, thank you. Do you want me to take questions, or I can take questions afterward, because I suspect people want to go, so it's your call.
Let's do a couple of minutes of questions and you can take questions.
Yeah.
Okay. So a couple of clarification questions here.
Okay. Yes.
So a few things about the chess application part, because I didn't get what is centipound rating. Are you talking about centipound loss of a move?
Yes.
Or so?
Yes.
We are focusing on one move and it's the centipound loss.
Yes.
And which moves are you looking at in the chess 960 game?
Moves that are feasible in standard chess. Right. That's the only move where
You're checking first opening moves. Is that right?
Yes.
How many moves are you checking?
20.
Only the first move. Only the first moves.
Only the first move. Yes.
The first moves.
Yes.
And what was the memory? It was the last classical game.
It's the entire vector of history of play on lichess.org. It's actually for many of our players, it's a vector of hundreds or even thousands of games of opening moves.
So that's your in memory.
Yes.
Okay.
Yes, and the average number of alternatives in memory is 5. 5 moves.
But for example, you count the pawn, the king pawn going to.
Yes.
That you identify regardless of where the king is located, or do you
No,
always
no,
call
no,
it the same?
no.
So it goes by
Yeah, yeah.
location or
By location, yes.
But that's not the right thing. I think you should do it. I mean,
We-
it should be relative to where the king is. I mean, I want to move my king. If my king is now one,
Yeah, no, this
one
is-
way, it's the same move.
Yes. No. We check, the way that we think about it is if your theory is true, then when I flip the standard board, so a mirror image now on the column, right? That only the king and the queen are switched, right? You don't see an effect of the people do not switch, which is.
That's not enough because if the king is on.
It's
okay,
not enough, but that's what we have. Yeah.
But if you have so many, how many data points you have per person? You said.
Oh, you mean the memory?
Yeah.
The memory is millions of observations.
No, per person.
Per person, I think it's 100 to 1,000. The majority of players, yeah.
One more question.
The memory is very rich. It's based on a lot of plays.
Yes.
So this is not in your design or anything.
No.
These are actual games that players chose.
Yes.
Better memories are used there. Because
Yes.
these moves, the real players, they are not trying to obey the model. They are just playing chess.
Yes. So that's
So the memory already has built into it some optimality. Is that
yes.
because of the memory? Okay.
Yes, but it's optimality that it doesn't disappear, but it's optimality that is not working in chess 960, because even slight changes in the positioning of the moves may have a large effect on how likely you are actually to win the game. You know, you could make a first move and that's it. You lost this game. Yeah.
In the 960, the players that played 960 in the past, did they have the random initial position or the correct initial position?
Players who, no, what we see is that
What's in the memory?
in the memory of players,
Look at the memory, the statistics of the memory.
how many alternatives?
How did it get?
Each time it's different. Each time it's randomized. In each game, the first order is randomized.
The first position is randomized.
Every
Yes.
time.
So it's
Yes.
the optimality in the randomized game.
Yes. Yes.
I'm playing chess.
Huh? No.
Moving the pawn that
No.
allows the
Yes.
bishops.
Oh no, we said what? Okay, so I'm gonna stay here. So if people have questions,
Let's
yes,
continue with the
yes,
conversation offline, and
yes.
thank
Thank
you
you.
all very much.
Thank you.